Yes.
Right. So I plan on spending, say, the last 15 minutes of class talking about some of the homework and some of the issues that you might be having. The first hour or so, we're going to be talking about chi-squared today. I will on Thursday though, because some of the stuff we need to talk about before you can actually do these types of problems probably going to take the entire time, and maybe a bit of time on Thursday. But what we've been going through so far is we've got a one sample t-test, and we've also got a one sample uh, prop z test. So these are, you have one group and you want to test it against a known value or a hypothesized value. Then we got into two sample t-tests. And then a two sample prop z. So these allow you to compare two different groups if you wanted to. And then if we continue on with this pattern, and we're going to get to this after the first exam, we can talk about ANOVA. If we continue on with the two sample or with the proportions and all that, we get into chi-squared. And if you're in a fraternity or sorority, you know that that's a chi, right? And not a chi or a chai. Well, we can call it a chi-squared. Once we've got done with both of those, we can talk about linear regression and then a logistic regression. Uh, when we're talking about these three up here, everything that we deal with is basically going to be groups or categories. When we deal with our regression models, we can look at pretty much anything, which is a lot better. So if we're thinking about what's going on here, these two methods can actually do exactly the same thing as ANOVA and the chi-squared, as well as the two sample t-test and the two sample prop z tests. So then when you ask the question, well, why don't we spend more time talking about these? It's because most of the time, when you read articles, the people that are producing those articles have no idea how to properly use these things or what their background is. So they do a lot of this sort of stuff. Uh, like I mentioned last time, a lot of the example problems I have are based on what? Anger, rage, hatred for people doing things the wrong way. Today won't be any different. Uh, so with the chi-squared tests, what we end up doing is we can break it down into a bunch of different categories. Sometimes these categories are actually meaningful. Sometimes these categories are created not because of some scientific theory, but because someone thought, I guess this is good enough here. So what ends up happening when you look at a lot of different chi-squared tests, they'll look at variables that are in fact continuous, like say age, and they will break age down. Instead of being a continuous variable, they will decide we want to look at age as various groups, like say 18 to 21, 22 to 25, 26 to 30, or something like that. If you know about logistic regression, there's absolutely no reason at all ever to do that. But again, a lot of times the people that are doing some of these tests don't know about it or figure, well, these other people did it this way. I guess I better do it that way as well. With the chi-square test, a lot of times the way that you're going to see it is it's going to be broken up into, say, 4 boxes. We can call these cells, and we can look at this as, say, did students pass or did they not pass? So when I say not pass, what does that mean? They took the class and either dropped it or failed it, okay? So they didn't pass the class. And then we can look at, say, Professor A versus Professor B. And what's going to happen is we're going to see, let's say Professor A taught 200 students, Professor B taught 300 students. We can now take these and break them apart. So let's say 125 of Professor A's students passed. That means 75 did not. We can say, I don't know, let's say 150 of Professor B's students passed, and which would mean that 150 of Professor B's students did not. And then we get to add these things up. So we have to have column totals and row totals. So in this case, 125 plus 150, 275, 75 and 150. It's going to be 225. And then we also need to talk about the total, which in this case is going to be 500. So with a table like this, we can now go in and do a chi-squared test a couple different ways. And basically what we're looking for when we have or do these chi-square tests, and I'm going to say this is chi-squared calculated, so this is based upon the data. We look at the summation of observed minus expected squared divided by expected, and this goes for n equals, or I should say I equals 1 to n. So these are going to be i's out here. So when you look at that formula, so using a couple different Greek letters here, but hopefully you all remember from your Algebra 1, Algebra 2 classes that the symbol right here is sigma, and this just means sum or add, right? So what we end up doing with this is we look at it in terms of uh, what did we expect to see, which is what these E's are, versus What did we actually see? Um, what we actually saw, that's just basically the recorded data that's in here. The expectation for what we should see, that can come from theory, that can come from the data, that can come from outside sources, and we will look at a couple different versions of this. If we have absolutely no idea what should be going on in here, okay? We can actually go and use the data to figure out what the expected value should be in every single one of these spaces. The formula for that is a bit. But what we have for any one of these, so E sub I, the expected value, and again, this is assuming we have no idea what we should be seeing here, other than this is what we saw. Our expected value is going to be the column total times the row total divided by the total. So in this case, the denominator in all these fractions is going to be 500. And just as an example, if we want to calculate the expected value for, say, E1 here, it's going to be 200 times 275 divided by 500. So we can go in, we can calculate all these values, and then we compare what is our expected value versus what we actually saw. And then we go in and try to calculate, is there actually a difference? Did we get something different than what we expected? And again, this formula is for when you have no idea what's going on. Uh, when I was interviewed for a position working at, or work that would have been working as a data analyst in a criminal justice research project, they wanted me to analyze data looking at recidivism of people. And I looked at it and said, uh, sure, you just use a logistic regression for that. They looked at me with horror. No, we need to use chi-squared. And I asked them why. Because that's how you do it. Like, what theory you're basing this on? Well, that's what all the papers do. So we went in and did it their way and found that quite literally there was no association, there was no nothing of significance happening between the data. And then you look at some of the papers that are out there that look at the exact same data, and they were able to find statistically significant differences. And part of the problem was the people that I would have been working for didn't know what to expect. They had no clue about the data other than this is what we have and this is what other people have done with it. Had uh, say these researchers been talking with uh, whoever about uh, this recidivism data, they would have said there doesn't seem to be a correlation, so this project is not working. But because they uh, didn't know any better, they had no clue what was going on, they used the worst possible method to analyze the data, and then it came back and bit them in the butt. So if we want to try to do this for this data here, it is an evolved process, unfortunately. So if I'm going to be using the graphing calculator, this is just typical stuff. So I need the row total, so 275, times the column total, just 200. I then need to divide that by the total, which is going to be 500. So we expect 110 people to be in that particular cell. You can see that we actually got 125. For the next one, 200 times 225, then divide that by 500. Here we find that the expected value is going to be 90. Going to this guy right here, so Professor B pass, we've got 275 times 300 divided by 500. So we expect 165 people in that group. And then for the last one, we've got 225 times 300, and then divide that by 500. And we expect to get 135 people down here. So one of the things that I would like to do is actually try to come up with a Excel spreadsheet for doing these things. The problem is uh, I can show you how to do it, but because these tables can take so many different forms, I can't give anyone, say, a generic calculator like it did with everything else on that exam one calculator thing. So if we want to see how to do this with Excel, we can do that. And I will make sure to actually share this particular screen. So again, we already know what all these things are going to turn out to be. So I can say Professor A, Professor B, then pass. I'm going to say not. These are going to be the four cells that we were just looking at. And I'm going to say over here, these are the observed data. Can copy this and say paste it over here. This is going to be the expected data. So looking at the observed data, again, 125 and 75, then 150 and 150. So to make this generic, because one of the places I taught at, they actually put a question like this on the final exam. When I saw it, I told the professor that wrote the final exam, I know exactly how to do this. I know how to use the calculator to do it. And it's still going to take me 10 to 15 minutes to do it. What chance do my students have of getting this one problem done and everything else during the exam? The answer was, well, that's part of the exam. If they can't get it done, or if they don't decide that they can skip something on there, that's part of learning. All right. So to make it as generic as possible, down on the bottom here, I'm going to say equal sum, and then open parentheses. And then I can highlight the area that I actually want to look at. And then I can close the parentheses. And then I'm just going to hit enter. So once I've got that into that one cell, I can actually take it, drag it over, and it's automatically going to change the references it's looking for to C2 and C3. Originally, it was looking at B2 and B3. Because I need to do, actually I don't need to do the same thing over here, so I'm not going to bother. But I also need to come in here and say equal to sum. And then add all these things together. Once I've got that, again, I can drop it down and it's going to automatically change the references that it's looking for. And now over here, what is the expected value for this? It's equal to the column total times the row total, and then divided by the total, which I forgot to fill out here. So again, I can put here, just drag this down, and it's automatically, again, going to change the cell references. Over here, again, column total times the row total divided by the total. Over here, again, column total times row total divided by the total. Anyone else getting that bored with me saying column total and row total over and over and over again? And then for the last time here, column total times the row total divided by the total. And there we have it. And what should be happening is when we look at the summation of these two things, it should be the same as the summation of these two things. When we look at the summation of these two things, it should be the summation of these two things. But there's a chance we could have different values. There's a chance we could have similar values when we go all looking across like this. I'm not going to worry about it. But now that we have all of this, we can, if I call these E1, E2, E3, and E4, or sorry, E1, E2, E3, and E4, we can start looking at the chi-squared value. Oops. So looking at it, cell 1, cell 2, cell 3, cell 4. So in each one of these, I've got to have observed minus expected, close parentheses, quantity squared, and I should be able to get away with saying divided by the expected value here. If I hit enter, I get this value just to check to make sure that I've got everything working right. I'm going to say 125 minus 110. Square that and then divide that by 110. So Excel's giving me a 2.05, calculator's giving me 2.04545. So tells me it's doing the calculations correctly. So the next one, open parentheses, observed minus expected, close parentheses, square that, divided by expected. And I can go ahead and hit enter. Do this again. So open parentheses, observed minus expected, quantity squared, divided by expected. Then for this final one, equal to open parentheses, observed minus expected, close parentheses, quantity squared divided by expected. And once I have that, chi-squared is the sum of all of those. So this is going to be equal to the sum of everything that I just looked at. And once I've got that set up, I can go ahead and hit enter. And that is the chi-squared calculated value for the data that we just looked at. Now, to figure out what's going on here, we have to compare the chi-squared calculated value versus chi-squared value that's normally in a table. There might be a way to look at something else. So chi-squared distribution, a lot of times chi-squared inverse. All right, we don't want that probability. So chi-squared distribution. Let's see, maybe that value, degrees of freedom, 1, cumulative, true. I haven't actually tried to do this yet, so I have no idea. If it's going to work. No, it didn't work. So we can just look up a chi-squared table. Some of these are a little bit better to deal with than others. All right, so what I've got here is a chi-square table. If I'm interested in a 95% confidence interval, with the data that we have, degrees of freedom is going to be equal to 1. Degrees of freedom is the number of columns you have minus 1 times the number of rows you have minus 1. And in the original data, we have 2 by 2. So 2 minus 1 times 2 minus 1 is going to be 1. So the chi-squared value that we want to use here to compare it to is a 3.841. And our calculated value is 7.57. Our calculated value is far larger than this. That tells us that at the 95% confidence level, there is a statistically significant difference between what we observed and what we expected. Looking at what we've got here, the 7 point whatever is above 5. So according to this, if we had the 97.5% confidence level, we are beyond that. If we're looking at the 99% confidence interval, or confidence level, we are beyond that. So what that's trying to tell us is that based upon the data we have, the outcomes that we've observed, so the stuff that we see right here, is different from what we would expect. At that point, once you found that there is a statistically significant difference between what you observed and what you expect, you then have to go in and try to do a little bit of a detective work to figure out what seems to be the most different. If we look at these individual chi-squared values here, that one happens to be like the largest one. And these two happen to be the largest two. And keep in mind, those two refer to the data points that are here. So basically what it's saying is Professor A seems to pass more students than we would expect. And down here, they do not pass, or they have fewer students not pass than we would expect. And is that useful information? Yeah. Some of the things that we can do with this is we can look at the data, we can see kind of what's going on with it and see what seems to be different. And then we can actually go back and try to uh, maybe we're looking at these and like we were talking about last time with myself versus the other professor, uh, perhaps there's an expectation that a certain percentage of students will not pass the class. Because I know for some of the engineering classes, uh, even if everyone in there does really, really well, there's an expectation that a certain number of students will not do very well. So I've actually known some professors that got in trouble because how dare you pass 80% of your students? The average should be more like 50. You pass too many students, you're too easy on them. You got to make the class harder. So perhaps that's the issue. So now you can go back and talk with that particular professor and say, hey, we think you're making the class a little bit too easy or too light of a grader or whatever. If they have all the exams to prove no, the students are just really that good. Well, okay. But if a professor is actually taking it a bit too easy on them, a lot of ways you can actually fix that sort of stuff. So again, going through all of this, what we've just done here is look at what is a chi-square test for, or when we have no idea what's actually going on here. We have no information, we have no theories, we have no ideas about anything. This type of stuff can come in to be quite harmful if we happen to be looking at other types of data. So just as an example of something that actually factually did happen, The numbers I'm about to write down are not correct, but it gives you an idea of what can actually happen with this. So how many of you are in human resources or thinking about human resources? Okay. So this is actually based on a story I heard about a particular tech company. I honestly don't remember what the tech company is, so don't ask. But I'm just going to make this a little bit simpler and say we're looking at software engineers and administrative assistants. And because with chi-squared we have to categorize everything, we're going to say, are they male or are they female? Now I'm going to come out and say, at this company, there are 950 software engineers and 50 administrative assistants. And when we look at the numbers here, I believe it was like 850 and 100, and then say 40 and 10. 850 plus 10, that's 860. 100 plus 40, that's 140. So our total here is going to be 1,000. Okay. Anybody want to guess what the story was about? So what ended up happening to this particular tech company, someone looked at these different ratios here and said, there seems to be a lot of discrimination based on gender in hiring. Just by looking at the data, does it look like there is discrimination in the gender of hiring people? If, or what they expected, so this is what was observed, what they expected when they look at these is basically 25 and 25, and what this is going to be, what, 475 and 475. So something like that. So you still get the 950 down here, you still get the 50 down here, but you're going to have 500 and 500. So they're the people that originally sued this tech company. They assumed that women are just as good at being software engineers as men are, which if you've ever worked with female software engineers or computer programmers, you know that's actually true. When you look at what they expected versus what they actually observed, I don't even need to do the chi-squared test to know that there is a huge freaking difference here, right? So tech company got sued, tech company lost, and had to pay a fine. Someone else came in, had some expectations. They assumed two things, not one. They assumed that women are just as good as men, but they also assumed that there aren't as many women in computer programming and software engineering as there are men. Now, if when we're talking about like if any of you have taken any classes in computer science, even now it's still going to be like 80 to 90% male, 10% female. When this went through, it was more 95% male, 5% female. So what did this other group do? So based on the assumption that women are just as good as men, but They only make up 5% of the workforce. They came up with different expectations. So I'm gonna go back to my graphing calculator if I can get to it. So 5% of the 950 people. So there should have only been 47.5, call it 48 women that are hired to be software engineers based on the two assumptions. One, women are just as good as men, and two, women only make up 5% of students that were taking computer programming and software engineering. We can go through, do the calculations, or do the rest of the calculations. But what happened the second time? Same tech company got sued a second time for gender discrimination against men. First time they got sued for gender discrimination against women and lost. Then got sued again for gender discrimination against men and lost. So if we want to fill out the rest of this, so this would be what, 950 minus 47.5. And then for whatever we have over here, I don't know that it really matters at all. But if we wanted to say 25 and 25 or whatever. So now if we take these new numbers, put them into our Excel spreadsheet, try to zoom in as best I can on these. So, and I will say with Excel, I've got these formulas in here. If I just start typing these numbers in here, it's going to eliminate those formulas. I don't have any problem with that because I know how to put them in here. If all of this stuff is like brand new to you and you're not sure about yourself, you can actually take and basically highlight everything we've got. Then I'm just going to copy it, open a new sheet, just paste it on that new sheet. And now I can plug in the values that I have. So this is going to be 850 and 100 and 40 and 10. Over here, this is going to be the 902.5, 47.5, then I'm say 25 and 25. And now looking at the values that we have here, keep in mind that this value here refers to what we had originally, or like we can call it cell 1. This refers to this particular cell. What are we noticing about the value here? We already saw in the table that even at the 99% confidence level, so again, this is still going to be 1 degree of freedom. If we have a value above 6.6, we would say there's a statistically significant difference between what we observed and what we expected. And just that one cell completely blows away that number. Which means based upon the data we have here, uh, it's that one cell that seems to be the issue, which is kind of weird, right? But again, where did the numbers come from in our, or from this expected thing? Well, at the time, again, it was 5% of students in computer science and software engineering were female. That's where it comes from. So again, depending upon what is our expectation, depending upon what theories we might be using, depending upon what assumptions we make, uh, we can get vastly different answers for what we should expect to happen. And that's the whole idea behind this here. Now, if you're part of the tech company and you had something like that, what was one of the assumptions I made? Women are just as good as men, right? What if women are a whole lot better than men? Or what if they hired a whole bunch of women that were a lot better than men? Should we expect a company to hire the best candidate possible? And if the best candidate possible happened to be quite a few more women than what we would expect, should that be the case? I'd say absolutely. So this isn't, so this is like an interesting case study to think about. But like I said, quite literally, the people that worked at this tech company, or this tech company got sued 2 times for gender discrimination, once for discriminating against men, once for discriminating against women, and lost both based on what they were expecting. So if any of you happen to get into HR and you start seeing things like that, uh, keep in mind how many people actually applied for the job, how many people are available to apply for the job. And what's one of the things a lot of tech companies had been doing for the last, say, 10 years? Trying to hire more women, right? One of the issues that comes up with that is, at least at the time, because there were so few women graduating with these computer science and software engineering degrees, that in order for all the tech companies to have like the 50-50 split that was originally assumed, uh, literally every single woman that graduates for like the next 10 years would have to have 4 different jobs and 4 different full-time jobs simultaneously. Does that sound feasible? And does every single woman in, let's just say, for all the women in here, do you all want to work at exactly the same place to begin with? Right. So a lot of issues came up with that, and there are still the same types of issues. Uh, with computer science, though, it has gone from like literally 5% female to like 10 to 15% female. But until not only until women start graduating with say software engineering degrees at the same rate as men, and then it's going to take some time after that because you're still going to have people that have been in the industry for a while. You're probably not going to get to this uh 50-50 split like anytime soon. Maybe someday, but uh what would we, so again, what would we have to do in order to get that? Uh, either there are actually 2 ways that you could get even numbers of students like that, or sorry, even numbers of employees. And it basically comes down to hiring women no matter how good they are, just because they're women, and then putting them in to these positions. And just because of the numbers of women that would be needed, we'd be hiring a lot. You could even start hiring a lot of women that are have no computer programming experience at all and just give them the title. And companies don't want to do that sort of stuff. They want quality employees. So just something to think about. I've also heard other stories that were similar to that. Is that the case with all these other issues? Honestly, I couldn't tell you. Uh, who's my mechanical engineer? How many women do you usually have in one of your ME classes? Like three? Yeah. And I used to take some industrial engineering classes in the grad program over here. Uh, 40 students in the class, four women, so 10%. So this sort of thing is going to happen and continue to happen even with like engineering. On the other hand, if you look at biology, usually that's like 60 to 70% women. So in a case like that, so if we're talking about, say, biological scientists and administrative assistants, if we see something like that happening and we know that, in fact, 70% of graduates with biology degrees are women, now we know that there's truly an issue here. Okay. A couple of the other things that I've seen happen, and this is just to give us a idea of how this type of data can actually be displayed. So instead of doing a 2x2 box, I'm going to do 4 groups. And let's say we're looking at white, black, Latino, and other. And let's say a company has, say, 690 white people that are hired in. Uh, let's say 190 black. Trying to think, what are all the different numbers that I should actually be putting in here? I think that adds up to be 1,000. Let me check real quick. So one of the horrible things about trying to come up with the stuff off the top of your head. So 690 plus 190 plus 100 plus 20. Yeah, so that's 1,000. And let's say that this is a company that is hiring people for this particular or for these particular positions. There is no degree requirement. The only requirement is, say, you can work 8-hour shifts. So no, you could be a high school dropout. You could be, you could have your PhD in mechanical engineering. They don't care. There's no education required here, which means everyone is equally qualified. And if we know that, say, in that particular area, 70% of the population is white, let's say 20% of the population is black, or let's say 9% of the population is Latino, and 1% of the population is other. Just so we remember, there's 1,000 people there. We can look at this. We'll say that is our observed values. Our expected values, when we look at these. So I'm assuming here that we are hiring people without discriminating against anyone. What's a 70% of 1,000? 700. What's 20% of 1,000? 200. What's 9% of 1,000? Well, 10% of 1,000 is 100. It's 9%, it's going to be 90. What's 1% of 1,000? should be 10. Without doing this whole chi-squared thing, does it look like the numbers we expect are similar to the numbers that we were actually observing here? Yes or no? Yeah. With something like this, what we have to be careful of is degrees of freedom is equal to number of cells minus 1. For these guys, degrees of freedom, number of row minus 1 times number of column minus 1. So it's a little bit different calculation. Same basic idea. Uh, so in this case, degrees of freedom is going to be 4 minus 1. So it's going to be 3. We can actually go back, use our Excel spreadsheet. Even though it's not written out in a row like we have it there, we can put our numbers for what we observed and what we expected here, and it's going to calculate everything correctly. It's just that the titles that I have here and the titles I have over here are going to be wrong. But if I wanted to, I could say 690, 190, 100, which is already there, and then say 20. And then over here for our expected values, 700, 200, 90, and 10. Looking at the first 3 values right there, they all look fairly small. But looking at the one value that we have right there, if we go and compare that to the 95% confidence level, this is going to be with 3 degrees of freedom. So 7.8 versus, sorry, 7.8 versus 11.75. So we could come back and say at the 95% confidence level, we believe there is a statistically significant difference between what we observed and what we expected. And the issue here is the people that are in the other category, there are too many of them that were hired, essentially. If we were to say drop this down to 17 and put 1 extra person in all these, so you don't necessarily have to do this part, but now that we look at the value we have here, compare that against what we have there. That's now below. So we'd say at the 95% confidence level, we do not have enough data to suggest there is a statistically significant difference between what we observed and what we expected. What did I literally do here? I put 1 more person in all those other groups. So one of the things that can happen when we're dealing with smaller numbers like 20 versus 10, because of the way things are actually calculated, we can completely blow this up, make it look like it's statistically significant. But if we make some small changes, so literally 1 more person in all those other categories, and all of a sudden our answer completely changes. That tells us that there can be what's called sensitivity issues when we're dealing with data like these. When we last class time, we were looking at the comparisons of the two different proportions, and we got two different p-values. One of those p-values was assuming a normal distribution. One of those was for Fisher's exact test. Anytime you have small values in some of these cells, like we have the 10 right here, versus say the 20 that we had over here originally, uh, because of issues like we just saw, there we may actually uh, need to use the Fisher's exact test, which we'll talk about next time. Okay. It's essentially the same calculation. We just use a stinky little correction. And if I'm going to be honest, I don't remember exactly what that correction is. So, but again, what ends up happening if we have smaller values in these expected columns? If you look in the textbook, it says in general, if it's a 5 or less, I actually would go for, say, 10 or less. You should be using the Fisher's exact value, just because of issues like we just saw here. But this is also kind of a lesson that when you see that there is a statistically significant difference there, uh, if things change a little bit and you come to a completely different conclusion, maybe the conclusion you had originally wasn't that good of one to begin with. Just as an example, I'm going to put these back to where they were. And let's say instead we have 10 here, but we expect there to be 20 over here. Now that difference, or the chi-squared value for that one cell, is 5. But when we had it the way it was originally, 20 versus 10, all of a sudden it's a lot bigger. That again is telling us that maybe chi-squared test is a little bit too sensitive, and we should be using the Fisher's exact test. Okay. So with that said, I know there were some of you that were emailing me about the homework. So let's talk about it. Anyone have any questions about the homework? And while you're looking through on that, okay.
Lower limit. Line. Is that considered beyond the lower limit or the upper limit? Is it like right on the line? You gotta choose like that.
Well, technically, no, technically, nothing will ever actually be right on the line. Cause what do you mean? Well, so since I've got it up, just send out an email to everyone. There is another opportunity for extra credit. I still have the sheet for the first one, and I've been trying to get all the grades put updated. I was planning on doing it over the weekend and kind of got sick while I was at a conference. If you're ever going to be sick, make sure you're feeling horrible in a hotel room, right? That's the best. Yeah. So anyway, this is tonight. I forgot to post it earlier. There will be more options like this. Uh, go 6 to 7. You can do the meeting in person, or you can go on Zoom. If you are going to go on Zoom, make sure you log in with your actual name. And then in the where the chat thing is, just type in I'm from like DS302. That'll save everything. And they will actually give me a copy of the entire chat room so I can give everyone the credit they deserve. Uh, the meeting on this prediction intervals for individual treatment effects in a multiple decision point framework using conformal inference or conformal inference. That's a mouthful. But basically, what's going on here, this is going to be based on biostatistics and clinical trials. Uh, but a lot of times, if you're going to be working in business, uh, we need to know like the confidence interval. If we're going to try to predict an outcome, what is the prediction interval for that? How does that change as we go through the experiment, that sort of thing? You're all going to be dealing with that sort of thing. If you try to predict what's the temperature going to be 15 days from now, is your prediction for that, for the temperature 15 days from now going to change based on it's 15 days from now versus it's the day before? I would hope so. So that's kind of the thing that they're getting into. It should be applicable to forecasting and other things like that. But anyway, so your question was, right, so let's say two things. Uh, let's say we've got a confidence interval that just happens to go from 2 to 9. If so, this is you and your research. And let's say group A finds that X bar equals 3. Is 3 in that confidence interval? Yeah. So that means group A agrees with the data. We are up here, this gives us a conclusion. That we're going to reject H naught. So remember, every time we do any of these statistical tests, we're trying to do a hypothesis test. Hypothesis test, the basic the null hypothesis is essentially always it's the same. This is telling us that it's different. We expect there to be somewhere between a 2 and a 9-point increase in whatever it is we're dealing with. This group agrees with our data, but if we look at the margin of error here, and do you remember how to get that? It's the upper confidence level minus the average. What is our average here? 11 divided by 2, so 5.5. So this is going to be 9 minus 5.5. So that's going to be what? 3.5. This value is below the margin of error. But they're going to find that there's no significant difference. So we're going to say they fail to reject. I know it's weird. It's something that does come up quite often. Another researcher does the same experiment as you. They confirm your data, but they don't agree that they thought that there's a significant difference. So you said we believe there is a 2 to 9 increase in whatever this is. We believe it is a positive value. We're probably going to have a p-value, say 0.02, 0.01, something like that. Someone else comes in and says we didn't find a significant difference between the two. So is there a significant difference or not? That's where the science comes in. And one of the things we're actually going to see a little bit later on, we can actually work with the two original data sets and come up with basically a combined conclusion based on Group A's data as well as the original data. So you were asking, like, let's say they got what, a average of 2? Is that what you're talking about here? Huh? What about graphs? Mm-hmm. So like someone got 2. Well, in this case, if it's our confidence level is or confidence interval is 2 to 9, and you got 2.5, that's within this. But if it was someone got, say, 1.5, they're outside of this. If they got 2.0 exactly, uh, technically, that's never going to happen. Part of the reason is when we look at the data, I rounded that, but you're going to have it out to 50 million bajillion trillion decimal points if you wanted to. So that's basically never going to happen. But which problem were you talking about?
Yeah. 3 and 2.
On homework 1?
On the third, or the second one, look at those top 3. Or no, look at that one, the one by, yeah.
Is that average below the line or above the line? And then you've got these 2 other ones that are outside, right? So one of the things that these charts are supposed to do, uh, give you a visual representation of what's actually going on. If you look at what the original data was, that's how you go back and determine whether or not that's in bounds or out of bounds. Because there is this clear delineating value right here of 50. And let's say this data point was 50. Is 50 in bounds or out of bounds? In this case, it'd be in bounds. If this was 49.9999999999999, it's in bounds. It's 50.001, it's out of bounds. If it's sitting right on there. Yeah. So I would, well, yeah, yeah. Isn't this due, what, Thursday? Okay. Yeah, no problem there. Yeah. With these, what, anytime you're dealing with these QC charts, you're actually going to have the raw data to look at. These are just to give you an idea of, is there some sort of an issue that's going on? So, so are there any other questions?
Yeah. Is there exit tickets?
No, no. We'll do a chi-squared thing next class.
So we have our first exam next Thursday. Is that gonna be like pen and paper or?
Um, Well, I'm gonna give you an exam, then you get to fill out the answers. Um. Depending on things. You're probably gonna need to use Minitab. So make sure that you've got that or a good graphing calculator. All right,
Thank you.
what's up?
I've never had this happen to your calculator before.
Yeah. So anytime you get a note like that, it's telling you that you screwed up something. So what type of calc? Well, it looks like you just hit a negative.
There's
Oh,
nothing. Then I have another calculator and I want to know if it's well.
one way to take care of it. So there is actually a little battery that's right back there. So you might have to take out the screw, pull that out and put it back in.
Like I reset it pretty bad.
Okay.
And I'll use the one. Well, this calculator.
No, it's a lot of the stuff. Yeah, so that's definitely an issue. One other thing that you can do. There should be a button right there.
That's hard.
It might be underneath that, but there should be a button you can hit to reset it. So can you grab my calculator that's right there? So like on mine, if I want to reset everything, I can just hit that button right there. Your calculator should have the same thing. It might be in there. The reason it's on there is a lot of times if you have a student that's going to come in and say for testing on ACT, SAT, something like that, they might try to store all the answers or store formulas on the calculator. They're not allowed to have that. You hit the reset button without having to go and check everything.
Right.
And it just does like a basic factory reset. Everything that we do on the exam, you either a graphing calculator or your tab,
Okay.
one of the two will work.
Okay.
Okay.
Perfect. Thank you.
And you will have access to menu tab on the exam. So
Thank
Right.
you.
Quick question. How much work do you expect to show on homework? Do you honestly like the whole formula written out? And like, I assume you want the formula and like the numbers inside the formula, but do you want us like to show like,
well,
because like,
I-
for example, for MOE, do you really want to see like,
well, what I so since I'm still recording this, so the question is, like, let's say, again, this is the data that you have. Okay. You want to, and I ask you, what is the average? Well, you're going to come out and like basically the work that you're going to do, assuming you got a pen that works, is basically going to be like X bar equals 9 plus 2 divided by 2. So that's going to be 5.5. So that's what I expect.
okay.
If we're going to calculate,
Because I was thinking like for MOE, do you really want to see like me calculate average and then like subtract it? I don't know.
so like if you're doing MLE, again, that's about the amount of calculation that I expect you to have. So that's going to be, in this case, the 9. And then when you want the standard error, that's going to be or something like that. I know that you're doing these on the calculator, so I don't need you to do like do long division by hand. I know you're doing it with the calculator, but one of the things that happens is, and this is something that was actually just happening with my students that I was teaching yesterday. They add a bunch of things together, And it should have been 150, but they got 140. So now every answer they have after that is wrong because it's in reference to 140, not 150. They did everything on there correctly except that initial step. So by showing me that you did, you put those two numbers in to get 5.5. Cool. You did like those two numbers in to get 3.5. Cool. You did 3.5 divided by 2 to get 1.75. Fine. That's the extent of the work that I expect. When you do like the probability calculation, I would actually expect you to do it where you just write down NCDF to show me that what formula you're using. I know your calculator is doing it, or I know that Excel's doing it. But I want to know what is the low value. So in this case, it's going to be 3.5, a high value, a mean, and then a standard error. And then give me the value. Because again, if you tell me that's what you got and then you put it into your calculator and you get something different, this is telling me that you did the right calculation. You're just bad at transcribing. Yeah, maybe you have I'm not saying you in particular, but maybe you have a learning disability or you have a little bit of dyslexia or something like that. Or there have been times when I've inverted two numbers, so it should be, say, 0.571 and I get it as 0.175 or whatever. It's the same numbers, just in different order. This tells me you know what you did. If you get this answer wrong, that just tells me you copied down something incorrectly.
And I assume it's the same for the exams, right?
Mhm.
Yeah, thank you, Professor.
Yeah, yeah, since we're using computers and all that, I know it's doing the work, not you, so you don't need to pretend fake that.
I understand. Thank you.
With the algebra classes that I've got, I show them how to use a graphic calculator to get the answers. And then I say, now that you know what the answer is, now you can do the work. And if you start to see it's getting off track, you know to stop and reevaluate. And I've actually made a couple of mistakes in front of those students. And it's like a X or A should equal 5, and I get A is a 72/94. Where'd that come from? Go back, oh, there's my mistake. Yeah, start from that point and work forward. So that's all I'm expecting. I know you're using a calculator. I know you're using Excel spreadsheets. I know you're doing all that stuff. Just show me what numbers you put in and go from there. Because if you start off with that, then you say it's a 32. And then over here, you're using like a 98. And for the calculation here, it's 15. And what are you on? And try not taking that before you do the exam. Okay.
Of course.
All right.
That's it.